Okay, so I'm going to talk about decision support with energy system modeling today, and I'm going to draw on a couple of examples from the modeling software that I co-develop and that we frequently use in my group, which is Calliope. But I also want to use this opportunity to make some more general points about how I think we as modelers can provide useful decision support. And so I look forward to discussing that with you a little bit later. So we know that greenhouse gas emissions have to be dramatically reduced. And because the majority of these emissions come from energy, we have to eliminate energy emissions. And over the past decade or so, there's a general consensus that has formed that probably the best chance to do this is by shifting to renewable energy. That's primarily solar and wind power with a range of other technologies in a supporting role. Now, there are many questions, however, about how exactly to do this, which remain open. So for example, when we look at scenarios for 100% renewable energy from individual countries to the entire world, we see several orders of magnitude in differences in one crucial question: how much electricity storage will be needed to balance the variability of wind and solar power? So on the one hand, we have, like in this example, we have lots of disagreements about the technical implementation. And there's even more disagreement about what is socially and politically acceptable. This is an example from Switzerland. Now, you don't need to understand German to know what the big red 9 here means. Some people are worried that the pristine Alps will be plastered with wind turbines, and they're understandably unhappy about that. So there's also disagreement about what is socially and politically acceptable. And this is where energy system modeling comes in. Now, I should clarify what I'm talking about here. We have, there are things like market models that a trading firm might use. There are grid models that a network operator runs to manage the grid in a safe and a stable way. And I'm not really talking about that kind of modeling here. I'm talking about modeling to support policy and planning decisions on the global transition to zero energy emissions. So now, one issue is that we as academics, we're sometimes like, hello, people down there on the ground. It's quite nice up here in the tower. I'm just building my models, publishing my papers. In fact, my newest model has higher resolution than the real world. And me and all my modeling colleagues are super excited about all that. Well, people outside the tower aren't really listening to this. They're too busy worrying about decisions being taken down there on the ground, like how we have just 2 to 3 decades left to rebuild the global energy system from the ground up. So we need a ladder to come down from the ivory tower. And one way to get such a ladder as energy system modelers is that we're doing scientific work. On the one hand, we're publishing in the scientific literature, but we'd also like the questions that we ask and answer to be relevant for decisions that actually have to be taken right now out there in the real world. So for actual energy policy. If we can do both these things at the same time, then we're building this ladder that brings us down from the ivory tower to help support real decisions. One such question is that of self-sufficiency. Here are 2 recent examples where policymakers in a city or an entire country make self-sufficiency, energy self-sufficiency, an explicit aim. Now, we wanted to systematically investigate if that's actually possible, and if so, what the trade-offs are. We did that in a study published last year in Joule, led by Tim Tröndle. Now, let's start with a small part of the results. We run an electricity system model to design for Europe, a continental scale renewable electricity system. And of course, the model uses the best possible locations for wind and PV. So generation relative to demand is much above 1 in some areas, but it's much below 1 in many other areas. Now, this continental scale fully optimized system requires substantially more transmission capacity than today's power system. What if I don't like that? What if I don't want to build so many new transmission lines? Well, we can add a constraint to the model that each of these 497 regions must supply itself with renewable electricity on average over a full year. So on average over the year, supply and demand in each region have to be balanced. And that also works. As you can see in the bottom map here, most places now generate pretty much exactly as much as they demand over the year. Now, some regions here still supply or generate more electricity than they demand, and that's for sort of model internal reasons, because we have, for example, hydropower plants in some places that we simply assume continue to exist irrespective of what happens. But we can explore these trade-offs in a systematic way now. We can start again with the continental system, where everything is fully interconnected, so renewable generation does not have to be where demand is. And we're concerned with how total system cost changes. So let's just say that this initial continental scale system has a base cost of 100%, and then we look at relative changes. Now I can say countries have to be self-sufficient on average over the year. That is, we want each country on average over the year to supply as much renewable electricity as its electricity consumption, but the power grid still exists. So countries can still use interconnection to elsewhere to help balance short and medium-term variability. Now that means that costs go up a little bit. We can go further and we can say, well, not just countries, but each individual region within the countries also has to be self-sufficient on average over the year, but they can still use the grid to balance. And again, costs go up a little bit. Now we can go even further. We can say we're going to actually cut each country off from all other countries. So if we look at this map on the left here, then we're removing all of the yellow connections between countries. So countries now actually have to be entirely self-sufficient in terms of their electricity supply. Of course, that leads to even higher system costs. And finally, if we say, well, we're actually going to completely remove the electricity grid and each individual sub-country region has to be entirely self-sufficient, then costs go up even further. Now, we can also look at other things we care about. For example, balancing capacity. That's basically the amount of storage, hydro dams, dispatchable biomass fired generation. So technologies that help us balance the variability of renewables. Again, and that makes sense, if we keep enforcing stricter and stricter constraints on how self-sufficient regions and countries have to be, we need more balancing capacity because we can't rely on the grid to do this balancing of variability. We can look at transmission capacity. Of course, here, if we're completely removing all transmission, each region has to be self-sufficient. Transmission capacity relative to the base case is down to 0%. So I can now navigate this and say, well, maybe I'm happy to have 20% higher costs for regions to be self-sufficient on average if that gets me slightly reduced transmission needs. Now, this work was done by Tim Tröndle in his PhD, and you can see here some of the key features of the underlying model that Tim built with Calliope. Now, one key thing that I want to point out is that this model was purpose-built to solve this particular question. So because it's a question of self-sufficiency of political units, the spatial layout of the grid follows political boundaries rather than the physical layout of the actual transmission system. Similarly, we model just those technologies that we actually need to answer this question in assuming that we're moving towards a fully renewable system. Of course, the whole thing, code and data, is also available online under an open license if you go to that GitHub link. So you can see what maybe we're trying here. We're saying, well, we're not just solving a model and saying here's a cost optimal solution. but using the tool that we have, the cost minimizing energy system model, using this tool to really systematically explore trade-offs between different solutions. And we can take that one step further. We can look at another example. Here, this is the cost optimal deployment of PV and wind for a fully renewable Italian energy system. Now you can see here in this cost optimal deployment, you can see where in the country the model places PV and wind capacity. And I'm highlighting here Sardinia, because Sardinia actually gets a very large amount of wind capacity. Now you might say, oh, that's fine. You know, Sardinia, everyone is used to all the oil refineries being there, so they won't mind if we also add some wind turbines. But if we want political buy-in, then maybe this isn't the best way to go about doing it. So in this study, we first looked for a cost optimal solution given the constraints that we set up. And we then run an algorithm to systematically explore the decision space within a certain amount of cost increase over that cost optimal solution, looking for solutions that are different in their spatial configuration. So we're really focusing on the spatial configuration here. So we generate loads and loads of alternative solutions and then sift through them to look for interesting ones. Like, for example, this particular solution where wind power is a lot more evenly distributed across Italy. Now, in this case, this is good because Sardinia, we no longer expect Sardinia to host such an enormous number of wind turbines. But there are trade-offs. You can see that, for example, there's now a lot more solar PV capacity up in the northern part of the country. And we can look at all sorts of other aspects of these different solutions to the same problem, the problem being a clean Italian energy system. We can look at transmission, we can look at curtailment. Here we're also looking at methane and hydrogen production and how that flows around the country. And we have lots of very different solutions with respect to all of these aspects of the problem. Now, the challenge with this approach is that it generates hundreds of solutions, potentially thousands. We have a large amount of data. All of these solutions are full energy system configurations that vary across a range of dimensions. So it's quite tricky to analyze them. We have to focus on some things that we care about. One thing we did here was to say, well, let's think of some technologies that could potentially be problematic, like bioenergy because its sustainability is contested, or offshore wind because it's politically tricky. Then we can explicitly look for solutions that minimize the use of those technologies and see how that influences the solution space. So in this case, for example, we're plotting all possible solutions that our algorithm has found and looking at what this means for the use of PV in the solution. If we ask them all to minimize batteries, the use of batteries, you can see that overall the PV utilization goes down. We're shifting to the left in this plot. That makes sense because batteries and PV sort of go hand in hand. Their batteries are used to balance the variability of PV, but we still have a really wide range of the maximum concentration of PV in a specific region. So we still have a lot of spatial diversity in where we want to put PV, even if we even if we want to minimize the use of batteries. So we can use this sort of tool to explore what kind of trade-offs exist. And there's lots and lots more examples in the paper that I'm linking here. Now, this work really is the brainchild of Francesco Lombardi during his PhD. And it went well beyond previous work on near-optimal solutions by really focusing on this aspect of spatial variability in an energy system model. And in short, the method works like this. First, we start with a model of the Italian energy system, and we minimize costs to find an optimal solution. Then we introduce weights. And the weights are really the ratio between the capacity of technology at a given location to its maximum capacity at that location for all technology and location combinations. So basically, the more of something there is at a certain location, the higher its weight. We introduce those weights to the model, and then we rerun the model. Now we're changing the objective function. We're no longer minimizing for cost, but we're minimizing for the sum of all of these weighted capacity decisions, while adding the constraint that cost has to remain within a certain range of the optimum. Let's say we allow for 10% cost increase over the optimum. And we can keep repeating this approach, rerunning with this new objective, updating the weights, repeating again and again to generate dozens or more of different solutions that are different in their spatial configuration of the energy system. I'm not going to go into detail, but then we add a second step on top of this where we also explicitly minimize the use of specific technologies, which allows us to then generate even more alternative solutions, especially if we're thinking about these potentially problematic technologies, for example. What we end up with is hundreds or more of diverse, spatially diverse solutions to our problem. And we call these solutions spores, spatially explicit, now I forgot what it actually stands for. It was supposed to be a creative acronym, spatially explicit, practically optimal results. There we go, spores. And this whole method is implemented in the Calliope modeling tool, so it can be applied to any other model as well. Right, so these were two examples of using energy system modeling to look at questions with policy relevance. Now, the problem here is that we sort of put this ladder here, and we're just kind of climbing down out of the ivory tower and delivering solutions to what we as researchers think the problem is. Now, that's been called the loading dock approach to linking science with decision making. And it's not really ideal because it's basically us as scientists, as researchers, just showing up with a truck full of our stuff and dumping it. But we're not really quite sure whether we're actually delivering the right stuff. So we can go further than that. Indeed, energy system models lend themselves quite nicely to co-producing directly with users of the results of these models. And NREL, the US National Renewable Energy Laboratory, is doing just that. And I want to talk about this example a little bit. This photo is from Hawaii, of course, pre-coronavirus, from a project coordinated through the Hawaii State Energy Office. And in this project, they used a range of highly interactive tools to get very different stakeholders directly involved in the modeling process. So you have government agencies, NGOs, universities, companies, community members, all sitting around the table. Of course, this process takes a while to set up. It requires establishing trust, a lot of trust through time. But when you have everyone at the table, and you also have the model in there in the same room, you can really consider all the different dimensions of the problem: academic, regulatory, commercial interests. In this example, for example, someone from the community was then able to say, well, actually the land that you're highlighting here for new infrastructure is used for pineapple groves. So this really won't, this is really not ideal. And this kind of feedback can then directly flow into the underlying model. So in this example, NREL, they started by taking the Calliope modeling tool. They then developed a web-based modeling interface that allows you to edit and run models, display the results. They also built a second visualization tool that can then display model results from Calliope or alongside other data and outputs from other models. So there's lots of computer stuff happening here. But in parallel, there's also the people stuff happening. So at each step, people are inputting data and assumptions, taking results back out, updating models, rerunning models, analyzing and visualizing outputs. And the key is that these two are tightly interwoven throughout. So together, with the effort to also bring a wide range of stakeholders to the table, this then leads to real co-production of the resulting scenarios and plans. So rather than just saying, well, we'll put some wind turbines here, deal with it, this can then include considerations on where people actually would like those turbines to be. And we're working on something that goes in a similar direction for the European context in a project that just started last month. You can check that out on the website on the link I've included up there. And I'm also happy to discuss that later. So we're building ladders to reach this cold, hard ground of reality. And we discussed a couple of examples of how we could do that. Now, I want to take a step back and also think a little bit about what kinds of models help build these ladders. And to answer that question, we need to think about how models are made and how they're used. And luckily for us, there's actually some work that looks into this. So how are models made? I think this is a really interesting issue that we as modelers should be thinking more about. The key thing is that assumptions in energy system models often reflect or reproduce societal and scientific discourses. And often they do this in an implicit or almost hidden way. It's not made explicit. Example, including or excluding certain technologies like CCS, for example. I might say, well, I really don't like CCS. I really don't think it's a thing that's ever going to be important or that we should really consider. So I'll exclude it from my model. So obviously my model will never consider CCS to be part of the solution. This is a pretty obvious example, but it actually goes much deeper. It's really about the entire setup and framing of the model. So if you conceptualize climate change primarily as a market failure, then you will probably consider that a carbon price is one of the prime solutions to address this market failure. If, on the other hand, you're thinking about climate change more in terms of institutional or infrastructural problems, then you might follow, you might go for a more evolutionary economics approach and focus on things like technological learning or the diffusion of innovations. And either way, you're going to make a range of assumptions and you're going to bake those assumptions into the very core and the very design of your model. So it's actually quite important to ask questions like, is this particular model saying we really need CO2 prices? Is that just reflecting the implicit assumptions that the modeler used when embedding her worldview in this model? Or is this model really able to say something on this yes/no question with regard to CO2 prices? Now, again, recall, we're really talking about models for decision support to make this transition to zero energy emissions. In an ongoing European research project, some colleagues led by Diana Susse looked at how energy system models are used in policymaking. And what they found is really there's a two-way interaction. On the one hand, models are used in things like impact assessment, target setting, sometimes even to design or select policy options. But modelers are also influenced by policymaking. For example, again, in terms of the assumptions they make, in terms of the data they use, in terms of the study scope. And this is quite interesting, also combined with what I showed on the previous slide. I think interesting, but also a little bit dangerous. If I set up an energy system model with assumptions that implicitly reflect current policy, then my results are used to set targets. We're sort of going around almost in a kind of an echo chamber. And so that's why transparency in these kinds of models is so critically important. The transparency helps me as a modeler, but also helps the users of model results to actually examine, to look at whether we're actually happy with the assumptions, and to ensure that the model is really modeling what we think it's modeling, or what we would like to be modeling. So a lot has been said about transparency and the importance of open code and open data. For example, Robbie Morrison, made these arguments very well in an earlier lecture in the series. But I think there's also something separate here that's a little bit to the side, and we could call that maybe understandability, the ease by which somebody can actually understand what's going on in a model. I think that's also really important, and it's somewhat separate from the issues of open code and data. So since this talk was supposed to be about Calliope, I can also talk about Calliope itself a little bit. That's this idea of understandability was one of the goals from the start, to sort of keep energy models human readable. You can see an example here defining combined cycle power plant technology and the various assumptions made for this technology. But remember, we want to be able to understand hidden assumptions in the model. And so for this kind of transparency, I think this kind of understandability, the ability to actually understand what's going on inside a model, is important, in addition to also having open code and open data. And I think one way to get to this ill-defined, this rather ill-defined concept of understandability is by simplicity. So making it easy to really rapidly build models aimed at a specific question. I think this is one thing that can help keep models simple, which is also why Calliope is designed that way to support that process. So basically with Calliope, the idea is that all you have to do is plug a couple of Lego pieces together. And you can use those Lego pieces to build a model of a district in Cambridge, or you can use it to build a model of the Kenyan energy system. To me, the key is that the tools that we use should support us. The tools that we as modelers use should support us in designing models that are as simple as possible to answer the question at hand, whether that question is designing a district energy system or assessing policy impact in the Kenyan coffee sector. So we'd like to end up with simpler models that are designed to help users understand their embedded assumptions by being readable for these users, and using open code and open data to help support those aims. Right, and that's really all I wanted to say. Here is a little summary of some of these points. My email address if you want to get in touch. And finally, also the Calliope project is really a collective effort across multiple institutions. So a big thanks to everyone involved, as well as to the other colleagues that help think us about these issues. So I'm very happy to take questions now or to start the discussion. Thanks a lot.